Okay, a question's been asked about what top hat means when they talk about torsional and steric strain and what the difference between those is. And so let me try and explain that. We will start with the figure 5.8 in your textbook, which looks like this. And you can see that they are looking, if you look at both the eclipsed and the staggered conformations, they have both torsional. Then they say, well, this one has both torsional and steric, and then back to torsional, and down here you have steric strain. So let me try and explain what they mean by those two terms and what the difference between those two terms is. So note, let's start with torsional strain. So you can see the torsional strain is only shown in the eclipsed versions. Now, their eclipsed version, I think, leaves a little bit to be desired, because if you're writing a Newman projection, the front carbon and then the back carbon, I traditionally write my eclipsed conformations. I try and show a little bit better that indeed those groups are right on top of each other. And so what this means is, this means in a sawhorse projection, which would be you over here looking at that molecule, that those bonds would be in the plane. It's a U shape in the plane, and then there'd be a bond coming towards you, and then bonds coming away from you. And if I'm over here looking down this bond, I'm seeing the Newman projection. And if I'm looking at the side, I'm seeing what's called a sawhorse representation. So, first of all, what's the torsional strain? Well, the torsional strain only occurs in the eclipsed conformation. No matter what the groups are that are basically parallel to each other and are eclipsing one another, that leads to a torsional strain where this cloud of electron density is basically repelling each other. So there is a torsional strain that causes these hydrogens to try and move away from each other as much as possible. So instead of this being an unstrained system, you get a little bit of repulsion of the electron clouds of the hydrogens pushing away from each other. And that's going to happen even if this molecule was ethane with 6 hydrogens on it. In the eclipsed conformation, you would still have the torsional strain, because those hydrogens are as close together as they can get, and so those clouds are going to repel each other a little bit, and so you're going to have these bonds kind of open up to be a little bit wider than 109.5. So that's what they're considering to be torsional strain, is when the hydrogens are eclipsing each other, or if the hydrogen is eclipsing a methyl group. So for instance, if I put a methyl group, if I made one of these a methyl group, there would still be torsional, there would still be torsion strain here. But notice that in eclipse conformation, you've got to have two groups that are eclipsing each other. So the best case scenario is 2 hydrogens. The next best scenario is an alkyl group with a hydrogen. And so that's what they're saying is torsional strain. Now, if we go back and we look at what they call steric strain, notice that steric strain occurs in the eclipse conformation when 2 alkyl groups come together. And down here in the staggered conformations, when the two methyl groups, when two non-hydrogen groups are gouged to each other, is the terminology here. So if we go back, the steric strain would occur in an eclipsed conformation. The steric strain would occur if I had two non-hydrogen groups eclipsing each other, because now those methyl groups are going to be even larger clouds of electron density. Let me write it out as a sawhorse here. Okay, you would have your CH3s, and then your hydrogens, so these even larger clouds of electron density due to the methyl group are going to be as close as they can be to each other in the eclipse conformation. And so this will lead to the same type of sort of opening up of the angle. In other words, these two are going to push away from each other as much as possible, and they're going to cause that angle to become more than 109.5. So this is going to be greater than 109.5. And so the methyl groups are going to basically push away from each other. So that's when the two non-hydrogen larger methyl groups are eclipsing, and now what they're saying is, well, the fact that they're eclipsed leads to the torsional strain, but then we also have the idea that we have methyl, or what I would consider to be non-hydrogen groups that are larger, and those groups are leading to what is called steric strain. And steric just basically means that we have larger groups that are basically nothing more than electron cloud or clouds of electron density, and those larger groups now, the closer they get, the more they're going to repel each other, and so this bond angle is going to open up well past 109.5. Up here, maybe a little bit more than 109.5, but down here considerably more. So what they're saying is that when you have eclipsing conformations, that's when you get the torsional strain of having the groups as close together as they can get. The steric strain is when you have non-hydrogen groups that are kind of repelling each other because they're clouds of electron density. So the steric strain would also show up in a staggered conformation whenever two non-hydrogen groups are next to each other. And what I mean by that is the group on the front and the group on the back are next to each other. This is called being gauche. And so these groups then, this would be an example of steric strain. So in other words, as those groups get closer together, because they're large clouds of electron density, they're going to repel each other, and so that's going to lead to the molecule being less stable, which is what both the torsional and the steric strains cause, is the molecule to be less stable than it would be if it didn't have those strains. Okay, so this steric strain can occur in both the gauche, whenever two non-hydrogen groups are gouged to each other in a staggered conformation, and the steric energy or steric strain can also occur when two non-hydrogen groups are eclipsing each other. In the eclipsing conformations, even if it's two hydrogens, they're saying that suffers from torsional strain, because when the two groups are as close together as possible, that's what gives you the torsional strain. Okay, let me try and show you this with some models. Okay, so let's take a look at this, at the two staggered conformations of butane. So here is this is my butane molecule, and this energy scale at the left says that the most stable conformation is what's called the anti, where the two methyl groups are as far away from each other as possible. And we're going to call that, relative energy wise, we're going to call that 0. So if I change this into a space filling model that shows the actual size of the methyl groups, what you can see is that the methyl groups are as far away from each other as possible. And so that's going to lead us to a situation where the molecule is going to be as stable as it gets. Now, if I put in this energy bar, what it says is, the next highest energy conformation of the molecule is a little bit over 3 kilojoules per mole. And now what you can see is the methyl groups are now gouged to each other. And so this is the example of the steric strain. And you can see that better if I take my molecule and I turn it into a space filling model. You can now see that the methyl groups are basically really close together. Now, this program will not let me draw the eclipse conformations, but if you can imagine taking these two methyl groups here as they stand and lining them up so they're perfectly together, they're going to be on top of each other. And all of this is negative charge. So they're going to basically want to push open the bond angles. So let me go here and go back to this. They're going to want to take these bond angles and they're going to want to push, this methyl group's going to want to push away this way. This methyl group's going to want to push away that way. And so it's going to open up those bond angles. As if this was eclipsed, it would be both torsional and steric strain. Okay. I can try and show this a little bit better with model. So here's a Tinker Toy model of the butane. So if I put this into the anti-conformation, it's going to look like that. If we look down the Newman projection, it's going to look like this, where I'm holding the back methyl group and the front methyl group is pointing towards you. So there's no torsional or steric strain in this. If I make this methyl group gauche like this, these two methyl groups are now going to be close together to each other and are going to undergo steric strain because they're close together. If I eclipse them, now the methyl groups are right on top of each other, and so what they're going to do is they're going to repel and the bond angles are going to open up like this. These hydrogens are also close together, and so they're also engaging in torsional strain. But since they're hydrogens, we don't call it steric strain. We only call it steric strain for atoms that are groups that are non-hydrogen. Okay, so any eclipse conformation, you're going to have torsional strain between the groups that are eclipsing each other. And you're going to have steric strain between either in the eclipse conformation between two non-hydrogen groups, in this case two methyls, whether they are eclipsing or whether they are gauche. Of course, eclipsing is much worse, much more unstable than being gauche. So I think that's how the book is using those terms. So hopefully that helps in terms of differentiating between torsional and steric strain in the way that they're using those terms.